Okay, so welcome everybody once more to the official IAU G2 online conference series. As usual, this is about massive stars, and today is my great pleasure to introduce our next speaker, Takashi Moriya. Thank you very much, Takashi, for accepting the invitation by the Commission to give this online seminar. Takashi is both assistant professor at National Astronomical Observatory of Japan and adjunct research fellow at Monash University. He has mainly developed his career in Japan, but also spent almost 3 years between 2013 and 16 as a postdoctoral fellow researcher in the Arlander Institute for Astronomy at the University of Bonn. This was after completing his PhD thesis in May 2013 at the University of Tokyo, and the title was Supernova Interacting with Circumstellar Media. Among several other milestones of his career, I would like to highlight that he received in 2020 and 2021 two awards as Young Astronomer by the National Institute of Natural Science and the Astronomical Society of Japan, respectively. And also, as most of you know, he is at present elected member of the IAU G2 Commission on Massive Stars. So he's mainly working on theoretical aspects of supernovae and massive star evolution, trying to deduce unknown activities of dying stars by studying supernova. He's also working on the origins of weird transients like superluminous supernova, those found in recent large transient surveys, and also actively involved in several optical and near-infrared transient surveys to discover the most distant supernova, to unveil stellar and cosmological properties of the early universe. And this is what he will be talking about today. So thank you very much once more, Takashi, for accepting our invitation. Whenever you want, the floor is yours.
Thank you, Sergio. So it's great pleasure to introduce our works in this seminar series. So as was kindly introduced, I'm Takashi Moriya from National Astronomical Observatory of Japan. Before I start, I would like to introduce our observatory. So this is our observatory located in Tokyo. So this greenery like forest in a suburb of Tokyo. I am now in this building. So this is in Tokyo, but it's in suburb of Tokyo. So central Tokyo is here. It takes around a bit 1 hour or a bit less to get here. So as you can see, this is a housing area surrounded by houses. And so this observatory was, this campus is 100 years old. Before that, the observatory was in central Tokyo around there. But 100 years ago, they found serious light pollution in this area, so they decided to move outward. So they located the observatory here. Back then it was called Tokyo Observatory. But now, as you can see, we are fully surrounded by houses, so no way we can do any astronomical research in this campus. We have old telescopes, but they are not used anymore. We have some small telescope for public outreach, but still this is kind of headquarter of the observatory. So this is the Center of Astronomical Research in Japan. We run like Subaru telescope, ALMAR, and also we are running supercomputing facilities for theoretical astronomy and so on. And I am belonging to division of science. So in this division we focus on research activities. So people in Subaru telescope or ALMA, they need to run telescopes and so on. So some of them don't have much time to work on research, but in this division, we are supposed to concentrate on research activities. And here we have many supernova and massive star related researchers. And also we have several student and postdoc opportunities. So if you are interested in, of course, visiting or working together, please feel free to contact us, and we can discuss what we can do together. So that was short introduction about our observatory. If you have any question, please ask at any time. I don't see raise up hand button, so you can just speak up. So I'm going to talk about supernovae in this talk, and supernovae are transient phenomena on the sky. So if you keep observing a sky in many times, then you sometimes see a new star or new stuff appearing on the sky. So this is one recent example from 2023. So this is supernova called 2023 IXF. So this is one of the most nearby supernova in the last decade. So this figure is before supernova, and this figure is after supernova, containing a supernova. And there's one spot appeared on the right side. Let's see if you can identify where is a supernova. So this supernova was discovered by amateur astronomer in Japan, Koichi Itagaki, and he is like almost professional, or maybe better than professional in finding supernovae. So if he sees these two pictures, he can immediately identify new spot because he has all the picture of the galaxies nearby in his mind. Anyway, let's see if you could find it. So this is the answer. So there is a new supernova, and that was very spectacular supernova in 2023. So once it explodes and once we identify, then the supernova become bright for a while and then fades away. So this is one example of supernova. So there's several types of supernova showing different ways to different way to evolve the luminosity. But this is like I think type 1A supernova. Supernova typically get bright in time scale of weeks or so, and then it gets faint in a similar time scale. We not only have information on this luminosity evolution, but also we can take spectra. We have a diversity in the spectral properties of supernovae. Some shows silicon, and some shows hydrogen, and so on, and some shows helium, strong helium feature, and others doesn't show anything. And roughly observed fraction is divided in these kind of categories. So yeah, we know there's many different kinds of stars exploding as supernovae. So what are supernovae? So supernovae are known to be explosion of stars, and roughly speaking, we know there's two kinds of stars that explode as supernovae. One is massive stars, which we will focus in this talk. This is explosion of stars with the initial mass heavier than around 8 solar masses. So we often call these quark collapse supernovae because they are triggered by the quark collapse of the central iron core. Another kind of stars that explode is white dwarfs, and they are thermonuclear explosion of white dwarfs. So if they reach close to the Chandrasekhar limit, typically, so if the white dwarf is in a binary system, then so if the white dwarf is in a single star system, so if it doesn't have any companion, then it will just cool down, doesn't do anything. But if it has a companion star, they can get accretion from the companion star, or if it may be two white dwarf merging at some point. So the exact pathway to form the type 1 supernova white dwarf explosion has been debated, but we know white dwarfs exploding, and they are observed as so-called type 1a supernovae. And type 1 supernovae are known to be standardizable, so it can be a distance indicator, and it has been applied for cosmology. But anyway, we will focus in this talk about massive stars, massive star explosion. So why we want to do research, or why we want to know about supernovae? There's several reasons. So first of all, it is a major production site of elements. So when the universe was born, there were only hydrogen and helium and slightly heavier elements existed, but only those. And then afterwards, nuclear reactions happened in the central region of stars. And then in the end, thanks to supernova explosions, these materials will be released in the universe, and that will enrich the elements in the universe. So there's like, depending on theory, there's some differences in which elements were mainly produced in which sites, but mostly these relatively light elements are produced in massive stars explosion or white dwarf explosions up to rubidium. And then more heavier elements is mostly produced by other kinds of system like neutron star mergers and so on. But anyway, major elements we have is produced during the explosion of massive stars. In order to understand how these element chemical enrichment happened in the universe, we need to understand the supernova property as well. And also, as the supernova explodes, then they will release the energy to the surroundings, and that will trigger that will release a lot of energy, and that will trigger the star formation of next generations and so on. So this supernova explosion will be releasing the energy that will be triggering the evolution of the universe. And also, now we are in the exciting era of gravitational wave astronomy. And these neutron stars and black holes we observe through gravitational waves. Originally, they were massive stars, and then there will be, for example, if in order to form neutron stars, then you should have some explosions associated. So in order to understand these origins of neutron stars and black holes, we need to understand supernovae and which kind of stars will explode and form neutron stars and which kind of star don't, and form black holes and so on. These will be a fundamental knowledge to interpret the for example, black hole mass distribution observed through the gravitational wave observatories. So those are just a small number of examples that why we want to study supernovae and why we want to know them in detail. So in order to answer this question, it is important to know what kind of properties each supernova have. What's the general property of supernovae? What's the typical explosion energy? What's the typical ejecta mass they produce, and so on. And what we observe from supernova is, as we saw at the beginning, so this is one example of supernova observation in the G and R band. So there's nothing appearing, and then at some point, at some moment, supernova explodes, and then you will start to see the evolution in luminosity, and then it gets brighter, and then it gets fainter. And this is an example of light curve from a hydrogen-rich supernova. So it has a hydrogen, and that means the star had a hydrogen-rich envelope. So this is likely to be an explosion from red supergiant. So by studying this kind of hydrogen-rich supernova, we can understand the property of the red supergiants that are about to explode and what kind of energy will be released when the red supergiants explodes. So as I mentioned earlier, we have this luminosity evolution we call light curve, and also we have spectral information, which is also important to interpret the supernova. But in this talk, I will focus on the luminosity evolution, light curve evolution, because we don't have much time to discuss the spectral property in detail. Anyway, just from the light curve, we can infer many information about the supernova properties. So this is showing, these figures are showing how the luminosity evolution or light curve of supernovae are affected by each different properties of the exploding star and explosion properties. So if, for example, if we change the stellar mass of the hydrogen red supergiant from 10 to 18 solar masses, so then you have you see some effect, especially in the duration of the phases, where the duration of the bright phases will be strongly affected by the this different mass. So this is basically determined by the mass of the hydrogen-rich envelope these progenitor have. Then if you change the explosion energy, and then then you can have as the explosion energy increases, then you can have a brighter supernova. And also you can have this bright phase will get shorter as the explosion energy gets higher. And we know also that nickel 56 mass affects this luminosity evolution very much. This is because this nickel 56, which is produced during the explosion, is will decay to the cobalt 56 in about 8 or 9 days or so. And then it decays to stable iron 56 in about 100 days. So it's unstable nuclei. So they decay, and since this is produced a lot, so this will provide additional energy to heat up the exploding star, and that will affect how the luminosity evolution. Especially in the case of nickel 56, the late phase will be strongly affected by the amount of nickel 56. And what is also interesting is that depending on the circumstellar matter density, especially this early phase light curve is known to be strongly affected by the circumstellar matter. So if the supernova explodes, if there's a dense circumstellar matter, then the supernova will hit to this dense circumstellar matter, and there will be a strong shock wave that's basically emitting out of photons. So that will affect the light curve as well. So this shock is providing extra energy to illuminate supernovae. And if there's a dense confined circumstellar matter, that will affect early phases. And And then if the density gets extremely high, then it can be affected. The entire luminosity evolution can be affected. So these are like example of the property of stars and explosions that will affect the these supernova properties. And what we can do is we have these a lot of models with different explosion energy, nickel mass, stellar mass, and so on. So we can do fitting procedure using, for example, MCMC method and provide get some estimate on each supernova properties. And this is one example of this kind to estimate the explosion property of supernovae. And then we can get some distribution of the properties of these explosion. So this is one example of compilation of estimated property of hydrogen-rich supernova. So these explosion of red supergiants. So these are property of exploding red supergiants. So we can have, let's say, mass distribution of the supernova, and also you can have a mass energy distribution of supernova. One interesting thing probably is that we often hear typical explosion energy of supernova is quark of supernova is 10 to the 51 ELS. But actually, in recently, if you study a lot of big sample of supernova, then you tend to have explosion energy estimate lower than 10 to the 51 ELG. So actually, for at least for the red supergiant explosion, those supernova having 10 to the 51 ELG is relatively maybe rare, and maybe usually they tend to have relatively lower explosion energy than 10 to the 51 ELGs. And this is for red supergiant explosion. And for example, strip chamber of supernova, like type 1b, 1cs, they tend to have relatively higher explosion energy. But for the case of red supergiant explosion, the typical explosion energy may be below 10 to the 51 ELS. And another thing we found interesting by studying these nearby samples of red supergiant explosions are these early luminosity evolution. So many supernova surveys are finding supernovae just after the explosion, like in this case. So these are like non-detection, and then you catch the supernova within a day or two after the explosion. And then you can have the luminosity evolution from early on. And if you explode red supergiant progenitor, theoretically, then what we were expecting is that, so this is the light curve in the optical wavelength range. So if the red supergiant or supernova explodes, then it will be heated up by the shock wave, which passed through the progenitor. And then as it expands, it cools down. So, and then at some point, the temperature gets low enough for the optical luminosity to be significant. So what we were expecting is like, so this rise time in the optical range will be corresponding to the like expansion cooling time scale of this ejector to be dominating, to be cool enough to be for the optical luminosity to be dominant. So for that, typically for the red supergiant explosions, which have a radius of 500 solar radius or higher, it usually this cooling time scale should be 20 days or so. But what we found is that this type 2 supernova, the red supergiant explosions, actually the rise time is much shorter than 20 days or so. It's typically less than 10 days. So it was kind of it was not in good agreement with what we were expecting. So there's some discrepancy between the rise time we expected from the red supergiant explosion. But as we discussed earlier, if there's circumstellar matter, then that can increase the luminosity in early times, and that can explain the rapid rise we observe in the optical luminosity. So this is basically adding up a new extra energy source provided by the shock wave, which in the caused by the dense circumstellar matter. And this is from the luminosity evolution perspective, but we also have many cases where they get spectra in very early phases. And in the spectra, we also see the evidence of this kind of circumstellar matter interactions. So it is seems these red supergiant explosions tend to have a dense circumstellar matter, much denser than what we expected from the standard wind mass loss. So this is something illustrating what I have said. So this is the mass loss rate we estimated by modeling a lot of this kind of light curve, and then we can, for each supernova luminosity evolution, we can estimate the required circumstellar matter property, and that can be interpreted as the mass loss rate. So in order to reproduce this kind of rapid rise observed in type 2 or hydrogen-rich supernova, we need to have this kind of the mass loss rate of the red supergiants should be above 10, typically 10 to the minus 4 solar mass per year or above. But if we observe like red supergiant in the local universe and we estimate the mass loss rate, then that's typically less than 10 to the 5 solar mass per year. So these estimated mass loss rate from the supernova observation is much higher than what we know from the red supergiants. So this, in some cases, we don't see any, like some cases, it's they have a like slow rise, which is consistent with not having very dense circumstellar matter. But let's say 80% or so or more requires this kind of dense circumstellar matter surrounding the red supergiant star in order to explain these early phase properties of the light curves and also spectra. So this is very interesting because so this kind of forming dense circumstellar, which is confined to the red supergiant progenitor, you need to have mass loss enhancement shortly before the explosion of these red supergiants. But the core collapse, which is triggering the supernova explosion, is happening at the center of this very extended red supergiants. And mass loss is happening at the surface of this star. So this kind of mass loss shortly before the explosion needs to happen in decades or centuries before the explosion. So if we just take, let's say, thermal time scale, then that's much longer than the time scale we need to for the surface to know that something is collapsing at the center. So there should be some dynamical way that is triggering the mass loss at the surface, and that is making the dense circumstellar matter that is affecting the supernova properties. So this is what exactly happening is still unknown. So of course, so there may be, so red supergiant itself is quite loosely bounded system. So maybe we don't need to trigger any mass loss. There may be anyway material surroundings and so on. We need to have like 0.1 solar masses of material confined, located quite close to the supernova exploding red supergiant. So that can explain the light supernova light properties. So what we found from the supernova observation from the local universe is that there is, at least for the red supergiants, there should be something surrounding the exploding red supergiant, dense circumstellar matter surrounding red supergiant that is affecting the supernova properties. So we found this kind of the existence of dense circumstellar matter by observing these supernovae and then interpreting them. And then we found something is going on in the exploding red supergiants. So far, I have been, so this kind of light curve supernova property is obtained by optical extensive transient survey, supernova surveys. And but those obtained, these hydrogen-rich supernovae we have been analyzing is mostly obtained or observed in the nearby universe. So this is kind of redshift distribution of the known type 2 supernova. Then most of them are like in the local universe, some of them in the deep optical transient survey, some relatively high redshift type 2 has been discovered, redshift 0.3 or so. There's a few cases from Hubble Space Telescope which had a relatively higher redshift, but those are never confirmed, so on. So mostly the knowledge about type 2 or supernova property, especially for red supergiant, have been coming from from the samples from the nearby universe. But this has changed almost suddenly in last year when JWST started to explore the time domain. So this came from this JWST Advanced Deep Extragalactic Survey called JAYS. So this survey is basically to search for high redshift galaxies. So they didn't have any plan to do transient search. So they asked a lot of time. And then they said, so they asked too much time. So it was technically impossible to observe the field they wanted to observe in one time. So they were forced to separate this observation 1 year apart. So they just happened to have two epochs in 1 year separation, and that was required to get the data they needed. So they, by chance, got the data in 1 year separation. So then people, they thought, okay, we can do the image subtractions to see if there's any supernova or whatever appearing. And then suddenly, a lot of transient or supernova popped up in these images. So this region, black region in the black is the two epoch. So the main survey area of this JAYS survey, and they have a 2-year observation. So they observed in 2022 and 23. So they did image subtraction, and then this blue dots are supernova that appeared, that was in the data in 2022 and disappeared in 2023. And these red dots are showing the location of supernova, which were not observed in 2022, but they found something appearing in 2023. And then because they found a lot of supernovae, they asked for extra time to follow these transients, especially interesting one. And also they asked for spectroscopic time to get some spectra to confirm the nature of these transients, if it is supernova or if it is, and of course, we also want to know the spectral type if possible. So that was, so they had extra observation like epoch 3, 4, and 5. So that's the follow-up observation they conducted. And each observation they could reach 30 magnitude, which is extremely deep. Like typical deep optical transient survey goes like 24 magnitude or so, but this is like crazy deep. And so suddenly because of this data, they suddenly found a lot of supernovae at very high redshift. For example, this is a type 2 supernova at redshift of 3.6. Just to remind, the type 2 supernova we had with good data was up to 0.3. So like suddenly increased by 10 times in redshift. And they found type 1 supernova at redshift almost 3. These they also have a spectra, so this is kind of spectroscopically confirmed. And they also find broadline 1c, so this is kind of energetic type 1c supernova at redshift of 2.8 and so on. Suddenly, these high redshift supernova data appeared, provided from the JWST. And I am not going to talk about much about type 1a, but of course, if you hear type 1a supernova at redshift of 3, then many people think, okay, is it useful for cosmology and so on? So they plotted Hubble diagram. So this is so they not only found one, but some other redshift 2.1-ish type 1a were found by JWST. This is extrapolation of the lambda CDM. So these points are not used for cosmological fitting, but they just extrapolated the lambda CDM fit from the local nearby type 1a sample. Then it seems on the lambda CDM, which would mean that type 1a supernova maybe still work as standardizable candle at redshift of 3 and so on. But this is still the discovery is still only 2 or so. So we need to see what's the indication. And what is interesting here is that there were in the initial search of this, in the initial investigation of this JWST data, we found like 6 confident high redshift type 2 supernovae. And these, among like, for example, I'm showing the highest redshift ones. So these we have like 3 or 4 epochs sometimes. So we do the light curve fitting, and then these cases are clearly not type 1a or type 1bc. So these are by looking into the luminosity evolution, we are almost 100% sure it should be type 2 supernova. So type 2 supernova has a characteristic evolution in the luminosity. So we can like there's like plateau phase and so on. So we can relatively easily tell if it's type 2 or not by from the light curve. And in some cases, like in this case, I'm not showing the spectra here, but we have a spectra and we are 100% sure this is type 2 supernova from the spectra. So we see clear hydrogen feature and so on, and this is no doubt, and this is redshift of 1.5. 6. And these redshifts are coming from the host galaxy. So we know the redshift, we know the luminosity evolution, and we are sure they are type 2 hydrogen-rich supernova, so explosion from red supergiants. So using this data, we can try to estimate the properties of explosions and properties of exploding stars by modeling this luminosity evolution, as I showed in the area. So it's like kind of similar procedure we do for the nearby type 2 supernova. But unfortunately, we only have like 4 epochs or so. So in order to constrain, for example, like a mass of the progenitor, then you need to have like an entire light curve. We need to know how long this bright phase lasted and so on. But we don't have such information yet, partly because this is at high redshift. So even if we observe for hundreds of days or years, then in the rest frame, it's still like tens of days because of the uh, time dilation. So for example, for redshift of 3, even if we observe for like a year or more, then you are still probing just initial 10 days or so in the rest frame. So we need to be very patient to get the entire information. But we still know like a luminosity of this plateau phase, bright phase, so that with which we can get some idea of explosion energy and so on. So we try to do estimate the properties as far as we can in this 2 high-redshift supernova sample, and this is the result we got. So yeah, each supernova and each redshift, based on the color, we can get estimate some reddening and so on. And as I discussed, it's difficult to estimate the mass. So it's basically we can't say much about the mass of the star, but the explosion energy we can get a relatively good idea. So these explosion energy we estimated. And what we found interesting is that if we see the estimated explosion properties, then as I said, typical explosion energy maybe 10 to the 51 L or maybe less. But we found like among 6 supernova, we found like 2 have a very high explosion energy, meaning the luminosity of the plateau phase is quite much brighter than what you typically have in the local universe. So that could, so this is the distribution I showed before, but that could mean that, so this is still 2 among 6 samples, so it's probably too early to say anything statistically, but we may tend to have relatively higher explosion energy at higher redshift, maybe. And this may be related to kind of metallicity, because at higher redshift, the overall metallicity could be lower. So this is, we don't know exactly, but for example, this may be related to metallicity, differences in the metallicity. And also what is interesting is that among like 5 or 6 spectroscopically confirmed supernovae, one was like broadline 1C. So this is also energetic explosion. So among small sample we have been investigating, the fraction of relatively high explosion supernova seems relatively high. But again, this is still, we need to have more sample to confirm this kind of statement statistically. One question, of course, is the higher explosion energy event gets brighter, so maybe it's easier to observe. But it's not likely the case. So this is showing the typical plateau luminosity, so bright phase luminosity of hydrogen-rich supernova as a function of redshift. So this is kind of what you typically, what the luminosity of type 2 supernova with typical explosion energy should be. And this transient survey has a depth of 30 magnitude. So, and so if it's the case, then we should be easily observe like type 2 supernova up to redshift of 4 or 5. And we are of normal kind. And we are finding type 2 supernova up to redshift 3.6. So our survey itself is not strongly biased to the bright events in this redshift range we are investigating. So if there were like standard supernova with standard exposure energy, we should be easily finding them. So it may be not the effect of the brightness, and it still may be intrinsic differences in the explosion properties. But again, we only have 6 samples now, so we need to increase, and there is a plan to investigate more about these supernova properties with JWST. So we can expect to have more data to confirm this kind of statement in the future. And also, if the supernova were observed in early enough, then we could estimate circumstantial matter properties. And in many cases, they were observed relatively late, so we can't tell much about the circumstantial matter. But in some cases, we could constrain the circumstantial matter properties, and that turned out to have similar mass loss rate to what we estimated from the local type 2 supernova samples. So this kind of mass loss enhancement or existence of confined circumstellar matter may be still common in the high redshift universe, redshift of 2 or so, which were probed by JWST. So this kind of mass loss may not be much related to metallicity again. And this kind of mass loss may be generally happening in the entire cosmic history. So it's about time, and that's what I have prepared. So the message I have is supernovae are very important to investigate in order to understand the cosmic history, but also, of course, in order to understand the evolution of massive stars. The supernovae is endpoint of the stellar evolution, massive star evolution. So from there, we can learn a lot about the massive star evolution. We can characterize them by modeling their light curves and, of course, spectra. I didn't talk much about spectra this time, but these 2 light curves and spectra are both important to infer the properties. And now we have a lot of supernova in the local universe from many different transient surveys. So we know we are starting to have good idea of the properties of supernova in the local universe. And then JWST is suddenly starting to open up the window to explore time domain astronomy at high redshift. And we are starting to have some idea of high redshift quark-collapse supernova properties. And they may be slightly higher. They may tend to have higher energy than the local universe, but still this needs to be confirmed in the future. And the circumstantial matter property as well. This CSM may be also existing in the high redshift universe. So that's it. Thank you for your attention.
Thank you very much, Takashi, for this very illustrative talk. And it's interesting to see how James Webb is opening the window to the high redshift universe with all these new observations. So now it's time for questions, if anyone wants to ask.
Hi, I would have one if that's all right.
Okay, go ahead.
Thank you, Takashi. Very interesting talk. I was wondering for the final point you made about the high redshift JWST supernova that we're seeing, that you're finding these higher energies. Is there, or I assume it's included in the modeling, but is there a chance that this could include degeneracies with what you mentioned with circumstellar medium, that maybe the masses are even higher than what we would expect at lower redshifts, the surrounding densities are increased, or do you exclude it and say it has to be differences in metallicity?
So especially for the circumstellar matter, we don't have like enough data to say what would be the differences in there. We start to see some possible, especially in some cases, they have a relatively high luminosity in the rest frame UV. That is probably coming from the circumstellar matter interaction, but we cannot tell very precisely what would be the exact mass or mass loss rate they should have had. So it's still, we can't tell exactly what would be if the mass loss is higher at high redshift or lower. We still don't know exactly. Yeah.
Thank you.
Any other question? Yeah, Lee.
Hi, Takashi. Thanks for the great talk. It was really interesting. So I was just interested in what fraction of the systems at low redshift do you require this circumstellar matter component to fit the light curve?
Yeah, so in order to fit the light curve, we need like it's 80% or so. We need to, so this kind of rapid increase in the luminosity is observed in 80% or so of the type 2 supernovae. And then if we take spectra, then around 50% or so shows this narrow feature, which is clearly indicating the existence of the dense circumstellar matter. So there's some discrepancies in the fraction we estimate from the light curve and the spectra, but maybe in order to see the spectral feature, the spectra needs to be taken in early enough, and then maybe the density threshold to see the effect in the spectra and the light curve may be slightly different, and so on. So there's something different in what we probe in light curve and spectra, but let's say 80% or so, up to 80%, we see the effect in this explosion of red supergiants, the existence of this dense circumstellar matter. So it's not like 10%, maybe not 100%, but more than 50%, 50 to 80% should have this kind of dense confined circumstellar matter at the time of the explosion in red supergiants.
Yeah, that's really interesting. Thank you very much. It's interesting that you can rule out that it's 100%, right? It's interesting that you have both of these cases. It's I'm not sure what do you have an explanation for what would be the case where a circumstellar component isn't required? I mean, how does that happen?
First, I mean, having no circumstellar matter is more natural in that respect because it's requires a lot of mass, like 0.1 solar masses, and mass loss rate should be extremely high. So what you naturally expect is no effect. But then we often see this effect, so there should be something going on, and how it's triggered or not, we have no idea. Maybe depends on mass. Yeah.
So could it be related to the explosion happening not in the red supergiant phase, but in the blue supergiant? Or this is...
So these have like a plateau phase. So this light luminosity effect, the CS circumstellar matter effect is only seen in like within 10 days or so. And then it becomes like usual type 2 supernova from red supergiant. So nothing peculiar if you observe after 10 days. So only something is happening at the beginning. And by looking at the light curve, you can tell the difference if the star is red supergiant or blue supergiant, because you expect to have quite different light curve evolution after 10 days.
Okay.
So these are for sure red supergiant explosion, not blue supergiant.
Okay, thank you. Please, Jahanvi, go ahead.
Yes, thank you so much. Thank you, Takashi, for the very nice talk. I wanted to ask a question regarding the plot that you showed about the magnitude. It is from your 2025 paper. Exactly. Yes, exactly. What is this inverted triangle, the purple one? Is it the upper limit?
This is upper limit. Yeah, sorry. So these are observed magnitude. So and this is observed frame, and I should have written which supernova this is. Sorry about that. But yes, and each color shows each band observed frame. It may be around redshift of 2. So rest frame is, this is like rest frame G band or maybe less. And then each band, and this is like 4 micron in observed frame. And these are rest frame optical. So this shows like luminosity and color evolution is definitely well reproduced and so on. Yeah.
Okay. And these lines are the model fit, right?
Oh, yes. So lines are model from the explosion of red supergiant model from the 16 Solar-mass red supergiant, and the explosion energy in this case is 1.5 times 10 to the 51 Ls. And that's the model light path.
Yeah. No, I just wanted to understand one more thing from this plot. So it seems like that we have kind of 2 peaks here.
You mean this one?
Yes. So I think it's near when the explosion is about to end, we have another peak, right?
So this is where, this is end of so-called plateau phase. So this at this moment, so in the I didn't explain this much, but so when the red supergiant explodes, there's a hydrogen-rich envelope, and then at the beginning, when the photosphere, so at first it cools down, and then photosphere reaches around the hydrogen recombination temperature around 6,000 Kelvin. And then this recombination wave goes through the hydrogen-rich envelope, and that phase has this plateau phase, so-called plateau phase, where you don't see much differences in the luminosity. And then when this photosphere reached at the bottom of this hydrogen-rich envelope, then you suddenly see the inner core, and that makes this strong decline in the luminosity. So from this moment, the photosphere, or where you look, is inside the core, former core. So this structure is coming from kind of structure from the hydrogen-rich envelope itself.
Yes, it's very interesting that after some time, you also see, after this peak, you also see a depth.
Yeah, so this could be kind of artificial because this is 1D explosion model, and we have a very clear boundary between hydrogen-rich envelope and the helium core in this explosion. But in reality, there should be Rayleigh-Taylor mixing and so on. So that will smooth out this kind of peak. So this, at least this kind of secondary peak we see could be an artifact of the fact that I am just using one-dimensional radiation transfer code. So this, I mean, this luminosity, especially this peak we see in the model, this needs to be carefully. This may not be real. So yeah.
And when there is, sorry, I don't want to interrupt. Please go on.
No, go ahead.
No, just as that once this peak drops, then we see another rise in the plot.
This is coming from the heating from the cobalt and nickel, and this phase is transparent, and the code I'm using doesn't treat this phase very well. So because it's optically thin. So this is again coming from numerical artifact. So this phase, this luminosity, it can be trusted, but as the time passes and as the supernova ejector gets relatively transparent, the code stops to handling doesn't handle the physics well. So there's several caveat we need. These small features we need to be careful to interpret.
Yeah, you're right. I think we need more data to actually see what the model is doing. Thank you so much.
Thank you.
Any other question? If not, I have probably naive question for the sake of my own curiosity, because it's the first time I've heard that. So you say that when you are considering time domain observation, the time span that you are observing is not the same. It's not sampling the same time in the event, or how was it? You say that you were covering more than 1 year, but actually it was 10 days.
Yeah, so this is redshift. So for example, if we probe, so in the observer frame, if we observe, let's say 300 days apart, almost 1 year, but if the object is in redshift of 2, because of the time dilation, because of a redshift effect, in the actual the rest frame time will be just 100 days, for example, because if it were the object is redshift of 2, so you need to divide by 1 plus z. So time will be extended as the redshift will get higher, which we never care if we are just observing the galactic object. But if you go very high redshift, yeah. So if you go high redshift, then the rest time in that redshift is different from our observational time. Yeah.
Okay, so in this sense, to have the next point of interest for your curves, how long you have to wait for the next observations?
So those are like typical redshift of 2 or so, 3, let's say, like then in order, so typically the type 2 supernova has the plateau duration of 100 days or so. If you want to probe entire plateau phase a redshift of 3, for example, then you need to observe at least like 400 days. But then, of course, you don't know when exactly supernova appears, so that will extend the required observing time. So at least 2-3 years, you need to keep observing the same field to have a proper light curve to analyze.
Good to know.
But they are kind of, JWST is starting to find it interesting, and we got time to keep monitoring this field for 2-3 more years. So we should be able to get much better data than we have now.
Let's see,
so we'll see
in a few years what is the result.
Yep.
Okay, so any final question? If not, I think it's a good moment to stop here. So thank you everybody for joining, and especially to Takashi for all the very interesting results and science that has shown today. See you very soon.
Thank you for joining. See you.